Welcome to our lecture on chapters 2 and 3. We've gone over some things in labs, and we'll go over more things in labs regarding rocks and minerals. So I'm not going to spend a lot of time on this, but I will give you a brief overview based on what the textbook talks about in terms of rocks and minerals. We'll talk about minerals and sedimentary rocks and igneous rocks, and we'll talk about the different kinds of areas on the planet that we find these things. And it becomes important as to what types of rocks are where as to what it really gets identified as. And when we look at things like I have here in the background, or if we look at the Grand Canyon, which I had in the background of the last one, or we look at sort of desert plains, or we look at tall mountains, we can see different kinds of structures that will lead to different kinds of rocks that we find on the ground. But these are also composed of different types of rocks and strata, which are sort of one on top of the other. So let me share the screen here. This that I'm sharing here will include chapters 2 and 3. So as we go through and do 2 and 3, they are separate files for you to look at. But these are minerals that we'll look at first. As we talked about in a lab, minerals are natural, so anything that's synthetic will not be a mineral. Artificial diamonds, we can make artificial diamonds, synthetic diamonds, but they are not defined as a mineral, even though they will be crystalline in structure. They are typically inorganic, although that's not always the case. The aforementioned diamonds. Diamonds are carbon, and anything with carbon is organic. So this is not a 100% thing here. They are solid. They are not liquid or gaseous. They are solid. Remember your 3 states of matter that we generally have. There are others like plasma, but for our purposes, think solid, liquid, and gas. Minerals are always a solid. So water would not be a mineral. Ice, on the other hand, can be a mineral if it's frozen and naturally occurring, because again, our definition is natural. So if you're making ice in your freezer, that will not be a mineral. But ice that forms in mountains and splits them apart, that will be a mineral. They have an orderly internal structure. That's the crystalline structure that I'm talking about. And then they have a definite chemical composition. So they're not just a hodgepodge of things. They all have a clearly defined essence to them. Rocks are, in fact, any naturally occurring solid that has mineral or mineral-like matter. And most rocks are aggregates or combinations. They're sort of mutts rather than pure breeds of minerals and perhaps other materials. So we have quartz and we have hornblende and we have feldspar, all of which are minerals. One of the things you can see is they have sort of these sharp edges, especially the feldspar here, some of the parts of the hornblende here. But you can see they're all mixed up in the granite here. So the granite itself has different mineral pieces to it. And if you want to learn a bit more about this, you can go to your PowerPoint and click on this link down here, and it will take you to a video that talks a bit more about that. You've probably studied this before in physical science or general science or physics in high school or other courses at our college. But atoms are the smallest complete particle of matter. I don't really like the definition in your book where it says it's the smallest particle of matter, because in fact, we can get subatomic and we can get quarks and other kinds of things. We're not going to worry about that. But the atom is the smallest piece of a particular type of matter. It's the smallest piece of hydrogen, the smallest piece of oxygen, the smallest piece of carbon will be an atom. If you get smaller than that, a proton or even subatomic there, that's still matter, but it is now generalized. A proton is a proton regardless of what element it's in. Atoms contain a nucleus, which has protons and neutrons in it, and then it has electrons going around it. Often you see this kind of solar system-like arrangement, but in truth, it's more like a globe. It's more like a hollowed out globe that the nucleus is in the center and the electron is going anywhere around the globe. But those globes, like a regular globe, are not sort of infinitely malleable in outward direction. So frequently what you're going to have are two different sizes or three different sizes or four different sizes of globes, and the atoms will have the electrons in particular shells. We call those shells. So protons are positive, electrons are negative. We arrange material on our periodic table. You've probably seen this in chemistry or physical science classes before. We have about 103, 104 elements overall, 90 of them naturally occurring. Some of them are rather tricky to work with, like uranium and plutonium. Some of them are standoffish. Over here in the far right-hand side, we have what are called the noble gases. We have some that are metallic, some that are non-metallic. Notice carbon here is in the non-metals. These are all the non-metals. All of these gray silver ones are metals, and they include things that you would think of as being metallic, like gold and silver and zinc and other kinds of magnesium, other kinds of things like that. And they are arranged by how many protons they have in the center. So hydrogen has 1, helium has 2, lithium has 3, carbon has 6, oxygen has 8. So that's how we sort of figure those out along the way. They can have more neutrons. So you can have carbon, for example, with 12 or 13 or 14 particles inside of it, but it will always have 6 protons. 6 of those particles will always be protons. There are more protons, it changes to a different element along the way. These shells that are around have electrons, and that's how they bind together. So we have the outermost is called the valence shell. That's where it sort of bumps up against other atoms and joins together. We have different rules for how that binding can take place. We're not going to worry too much about that in this class, but just know that we have chemical bonds of different sorts along the way. When we're dealing with ionic bonding, for example, what we're dealing with is sort of an electronic charge, positively or negatively charged ions. It has more electrons or fewer electrons, so they bind together because the opposites attract each other. So the arrangement, for example, in table salt, which is sodium and chlorine together, it's called sodium chloride. The sodium is a positive and the chlorine is a negative. So what we have are a balance between those. But that means essentially it is an easier thing to break apart in many ways. And the naturally forming crystal structure, which is a mineral, is halite. And you may remember from labs, that is one of the rocks that you can hold up and say, hey, you could lick this, and it would, you're not, don't do that, it's unsafe. But this is what you could actually use to season your French fries. They're not on my diet anymore, so I can't season the French fries. We have covalent bonding where we're sort of sharing electrons. So we've got 2 protons and 2 electrons, but they're sort of going back and forth in different ways around each other. We don't have any imbalance in terms of positives and negatives. There are many, many gases. For example, we have H2, which is hydrogen gas, O2, which is oxygen gas, will have this kind of bond. Then we have metallic bonding. This does contain ions. And what happens is the electrons just move freely between the different nuclei that are there. And that's one of the reasons why a lot of metallic substances are good conductors for electricity, because they're already naturally doing stuff like that. When we look at minerals, we have different ways in which we can just eyeball what's happening. Luster, how it appears in the light, color. This varies, and color is not really good for telling whether something's crystal or not, because we might have a lot of pieces of fluorite, for example, and they'll all be fluorite, but they'll all be different colors. Here, we can streak on what we call a strike plate. I showed you a couple of things like this. When we have pyrite or When we have graphite in particular, we can strike it and see that one gives us a much stronger impression than the other. Some are very hard and some are soft. Graphite in particular is rather soft. We have something called the shape or the habit. We talked about this in our lab, and we can see the different kinds of shapes that take place, including cubic and fibrous, this kind of stuff in asbestos, for example. As you can see, you're sort of pulling it apart. It would make some kind of good kind of sort of fuzzy fabric or some kind of good fuzzy filler for things, which is why it was used in the first place. Nobody knew at the time, of course, that would tend to degenerate and particleize into the air, and then you breathe it in and it gets caught in your lungs. So if you're around something like this in and of itself really isn't going to bother you, but processed asbestos can be dangerous. This in and of itself is not really going to bother you if you're just around it briefly to see. But again, we have a video that you can check out at the bottom of this. We have strength. We have the Mohs scale, M-O-H-S, Mohs scale. Some are very light and delicate, like talc and gypsum. You can almost crumple this apart with your fingers. You can certainly sort of rub it together and it flakes off into a powdery substance. That's where talcum powder comes from. On the other hand, diamonds up here, notice, and again, diamond is the carbon, so it would be the organic one, is the thing that scratches everything else. So when we're talking about minerals, there are different hardness possibilities with regards to minerals, but hardness by itself doesn't tell us exactly what's going on in terms of whether it's a mineral or not, because it can be soft as anything or hard as diamond. And then we have the strength in terms of how it breaks apart, and that can in part depend upon the bonds that are inside. And we get different kinds of cleavages, and we can get cleavages in 1, 2, or 3 directions that go at right angles or not right angles, or with our fluorite here, remember the multicolors, it actually breaks into 4 different directions. Muscovite, remember that's that light flaky stuff, almost looks like baklava in our tray of rocks. It's very, very flaky, very, very delicate, and it'll fall apart just by holding it up to look at it. Whereas other things like halite and calcite, you can sort of bang on the table and it'll damage the table before it damages the rock. Now, when we're looking at some, like quartz, we will often get irregular or conchoidal fractures. Conchoidal is sort of the spiral that you're seeing here. And these will tend towards different kinds of impact. So if you have a twisting impact or a twisting force on it, you're likely to get a conchoidal fracture. And that will happen, especially if you've got some kind of liquid that's happening. Magma or rushing water or other things can often break things apart in this direction. Specific gravity means, is it denser than water? Specific gravity of water is 1, so anything that is higher than that will tend to sink. Minerals tend to sink, but again, our muscovite, you're going to see that floating on the top if it's been sort of shaved into the thin sheets that we have there. Other properties include taste and smell. I don't suggest you do this too much, but you can think about sulfur. Sulfur is a mineral. It has a distinct taste and a really distinct smell along the way. The halite has a taste, and we also have different kinds of changeability. We have our refracting, whether light goes through it in different ways, because as the light goes through some crystals, it will change the way the light waves function. We use crystals frequently, usually synthetic crystals rather than natural minerals, for lasers. And we send the light through the crystal and it changes it, it focuses it, because you can play around with things like this. Then you also have magnetism. Many metals are magnetic, although depending on the conditions, you can magnetize almost anything. If you look at the sun, it has lots and lots of areas of magnetized hydrogen. Well, hydrogen isn't magnetic, it's not even a metal. But under the forces on the sun, it does become magnetized. That does not tend to happen very much on Earth, though. So that's something you would be aware of in astrophysics, but not have to worry about so much with regard to planetary astronomy or planetary Earth science. And then we have just the feel. You can sort of feel sulfur and feel talc, and it feels slippery. That's partly because the kind of powdery substance is coming off on you. Whereas if you feel the halite or you feel diamonds, it feels very, very hard. Then some will react to acid, hydrochloric acid, and give us a bubbling effect. Others will not. You can see one mineral here, calcite, reacting to the acid if you click on the link in your PowerPoint. Then as we're looking at rocks on Earth, we see oxygen wins 46.6% in terms of rock forming minerals. These are the 8 most abundant elements in the Earth's crust, and there are a couple of different sort of wiggle room kinds of things in these, because notice these are all 2 point something down here. But notice oxygen wins by far. That's because when we're talking about oxygen, we're not just talking about the stuff we breathe in and out. When we're drinking water, we're drinking oxygen, H2O. The O is in there, that's the oxygen. When anything rusts, that's oxidation. Oxygen has been leached into whatever it is we're seeing that's rusted or oxidized. So there's a lot of oxygen in our planetary system, not just in the atmosphere, not just in the water, but actually in the rocks and minerals that we have here on Earth. So remember that. Silicate minerals, notice again we have our silicon and oxygen. When you put those two things together, it's by far like, okay, thanks for playing everyone else. We'll take it from here. So silicate minerals are by far the most common. Of course, most of that is in the magma underneath us and in the mantle and down even into the core of our planet. Although by the time we get to the core, probably less oxygen there and more metallic elements that are down there along the way. But we can sort of see here we have a silicon-oxygen tetrahedron. We have silicon in the middle with different oxygens around. Notice this is a +4, these are -2s. So what we'll end up with is what's called a tetrahedra bond, where it's sharing different things. In terms of which is most common, our feldspars are most common. By far, it's the majority, 51%. They win the election, thanks for playing. All the rest added up together. But we have micas, we have clay minerals, which we don't often think of clay as being a mineral. We think about it as sort of compact dirt, but that's sort of disintegrated mineral kinds of stuff along the way. And then we have quartz. Quartz is pretty common as well. And these are some different ways in which we can look at the structures of these. Look at quartz down here. We can see it's quite an interesting structure internally. When we're looking at micas, it sort of looks like a lattice structure that is spread out like a sheet. When we're looking at hornblende or amphiboles, we see it's more like a chain, but it's wider than our pyroxenes up here, which are a simple chain. So we have different ones that are there. Olivine is an interesting one. We find olivine in lunar samples, and sometimes there's H2O locked in the olivine. So we have found just in the last few years, there's a lot more water on the moon than we ever thought, because we hadn't seen inside the olivine before, and now we have. So here are a couple of common minerals, silicate minerals. We have potassium, and we can sort of see the way it chunks apart. Down here we have feldspars, and we can see how those plagioclase feldspars just sort of break apart more like the quartz does. Then we have some quartz here, and we can tell again, the color is not what gives it away, because we have different colors of quartz depending upon the impurities that are around it as it's forming. And then we have some other light things like our muscovite, which just sort of peels off almost like plastic shavings along the way. And then the clay stuff, which disintegrates, but then becomes compacted very easily under anything that's weighty. Here we have olivine, rich peridotite, and it is often found in ocean crust. So we're getting deep, deep with stuff like this. And it also makes up mantle rocks, which is underneath all of the continents and the ocean bed. And then we have some others like augite and hornblende here. These are found in basalt kinds of stuff. If you look at, I'm going to stop sharing here for a moment. If you look behind me, notice the structure that we have here on the side of the lake that's coming off of the coming off of the waterfall that's down there. Well, this has sort of been eating away over the centuries, just like the Grand Canyon was cut through by the Colorado River. But notice the sort of the angularity here. These are basalt, and this is seen from Iceland. Surprise, surprise. It's me, so it's probably Iceland if it's me. And that is sort of chunky in this way. And then, of course, we have biotite and garnets. Garnets often are used for sort of fake jewelry, and we can find that in a lot of different colors, and it comes in some interesting crystal shapes that, again, will be good for jewelry purposes. Then we have some non-silicate minerals, including carbonates. Remember, anything carbon is organic, so it's not just that things that are inorganic are minerals. We do have some things like calcite and dolomite that are here, but then we have others, halides, including our halite, our salt, NaCl, sodium chloride, which is halite here. Then we have oxides. Guess what element is part of that? Well, let's see, O. We have O's in there, including ice. Hey, there's ice. Ice is listed as a mineral. Remember, if it is naturally occurring, it is a mineral. Here's just a clue for you as well. If there's a true-false question and it says, is ice a mineral? Go ahead and say true, unless it's putting some kind of qualification, because you'd get it from this chart, for example, where it's saying ice is in the mineral group. And we won't worry so much about whether in that kind of true-false question, whether it's not really trying to trick you. I'm generally not trying to trick you when it comes to true-false questions. Then we have sulfides and sulfates. They all, of course, have sulfur in them along the way. When we're dealing with sulfides, we have sulfur. Sulfates involve sulfur and oxygen. And then we have different elements like gold, copper, sulfur, silver, other kinds of things like that are just sort of by themselves. They don't tend to combine with other things too much along the way, so we call those native elements. Minerals are not renewable. Once you've used it up, you've used it up. So all those pennies that you're hoarding in your penny jars at home, that copper isn't being returned into the system anymore. But here's the thing, most of those are not copper anymore. They might be copper coated, but they're not copper anymore. We've sort of stopped using copper decades ago because it is a non-renewable resource. Things that are renewable include wind, water, anything agricultural, anything that grows, anything that does not grow, which includes anything metal, aluminum, anything oil and gas and coal. Well, you may remember from Mrs. Doubtfire, where he's talking about, where he's doing his little thing with the dinosaurs, and he talks about the dinosaur being dead and coming back as oil. Well, they're not making dead dinosaurs anymore, so we're going to run out of coal, and we're going to run out of oil, and we're going to run out of natural gas. Not tomorrow, not next week or next month, but we've got at most a couple hundred years left on our planet of these things. And it's not just going into the cars and energy. We use petroleum products for everything plastic. So one of the ways in which we've been driving up the use of non-renewables is by using plastic rather than glass. I remember from my childhood, most things came in glass bottles. It's hard to find glass bottles now. Almost everything's in plastic. most of those things should be recycled. Most of those things are not recycled, and that becomes an issue along the way. So when we're looking at these kinds of substances, we usually have to dig for them. We can dig really deep. Salt mines are often leftovers from seabeds or ocean beds that once upon a time were inland. We also have open mines where you're sort of digging down rather than having a tunnel in. You're just sort of stripping the top layers off again and again and again to get to areas. Depending upon how these are done, they can be very environmentally unfriendly if people prepare themselves properly in doing these kinds of things. They have a reclamation project so that when the mine is done, it can be reclaimed as a natural resource. In terms of chapter 3, we're looking at different rocks that are not minerals. We have a basic cycle. We have magma, which sort of crystallizes above or below ground into igneous rock. That's typically magma will be something that's been fired. So when we're talking about magma, we're talking about lava. We're talking about super, super hot stuff. Weathering also breaks things down. Sediment is the leftover stuff from the weathering. Lithification, this is the sort of pushing together under pressure, which we call compaction and crystallization, to form sedimentary rock. So it's sort of a buildup over time. Then metamorphic rock will be changed in some process. So it's not just being pressurized, but it's also being heated and changed in the heating. So think about, if you had to, think about an egg here. A sedimentary egg would be just the egg that's there. You could put an egg under lots and lots and lots of pressure. It's still going to be kind of stuff. But if you change the temperature, guess what? It boils, hard boils. Other kinds of things happen to it. You can see a video on the rock cycle here if you click on this from your PowerPoint. But this is the basic rock cycle here. So we have our lava, our magma underneath the surface, lava at the top. Essentially, magma and lava are the same, except when magma reaches the surface to become lava, when lava reaches the surface, it begins to interact with the water on the surface, the atmosphere, and other things. So that will change the aspects of it. And it will cool it off, obviously. It cools, it crystallizes, it becomes weathered, it becomes sediment that gets pushed down, and sometimes changed, sometimes not, by heat processes. And notice there's lots of back and forth inside here. It's not just a continuous loop, but it's a loop with a lot of loop-de-loops inside in different ways. So these are the shortcuts, and we can have different kinds of melts, we can have different kinds of heating, we can have different kinds of weathering at any stage along the way. So we have different kinds of magma cools for igneous rocks. Here's Mount Rushmore. One of the interesting things about Mount Rushmore, notice this stuff that's down here. This is actually a trash heap. This is the leftover from when they were carving the faces into the hills here. The original sculptor was going to have sort of like the whole upper body of these, certainly of Lincoln and of Washington, maybe not so much Teddy Roosevelt back here and Thomas Jefferson, but the rock is not as hard. This is not nearly as tough as, say, diamond mineral. The Mohs scale here is going to be very, very small in terms of how tough it would be if we were to use a Mohs scale kind of thing on here. That's why, contrary to popular belief, we're never going to have Donald Trump's face over here. We're never going to have Barack Obama's face over here. We're never going to have Ronald Reagan's face over here. We're never going to have it on either side because the mountain side is just too brittle. And they had to stop where they were because things were beginning already to fall apart. So sorry to all of you who have other favorite presidents, including the current one. The rock face itself just won't hold up to it. And that would sort of be a bad political thing anyway. If you carve your face into a rock and then it slides off, that's a bad omen. There is something that happened in New Hampshire there is a granite kind of structure, not too dissimilar from Mount Rushmore here, that had sort of an outline of a man. It sort of had sort of the profile, where if you looked at it as you're coming up the pathway, you look up at the top of the mountain, you would see the profile of a man. And this was so famous that it's actually on the state quarter for New Hampshire. That's one of the main natural things in New Hampshire that people go to see. Well, it fell off. It fell off about a decade and a half ago because the rock is unstable. The rock is unsteady. Eventually, these faces will wear away. And you put another face up there and they'll wear away much, much faster. From magma to crystalline rock, we have different rates of formation depending upon the cooling. Slower rates form larger crystals, faster rates can form glass and glassy type structures. So notice this obsidian here has a very glassy like structure along the way. So when we're looking at igneous compositions, lots of silicate minerals, not a surprise, because remember from our chart where we had lots of oxygen and lots of silicon, 2/3 of everything were silicon and oxygen. So that makes a lot of sense here. And we can sort of see in terms of how things are, in terms of temperatures going up or down, increasing the silicate material, up more silicate over here, less silicate over there. So that makes a difference in terms of things. And then we have our different kinds of sizes, shapes, and arrangements of the different minerals that are thrown together to make our basic rocks. But rocks will also contain holes and gas bubbles. This is where we were finding, as I mentioned before, the water on the moon inside the olivine pieces, because there are holes that are left over. And you'll probably see this if you pick up rocks like we have this one down here that comes out of a lava row. You can often see that kind of bubbly structure. Well, if it's completely contained, it can hold onto the H2O that's inside of there. We have granitic rocks, we have andesitic rocks, and we have basaltic rocks. And those different kinds will give us different kinds of mixtures. We'll do a lab that talks a little bit about this. Notice this one here. This is something that's probably, if you have a sort of chunk of like dried lava, you'll often have something like this that will float on water. Its specific gravity is less than 1. Remember, if it's more than 1, it sinks. If it's less than 1, it feels like a hardened sponge in many ways. And then here we can go from coarsely grained to glassy to pyroclastic, where it's beginning to fall apart in terms of the texture. And then we have our different mineral compositions up here. So different types of minerals that go into it. So if you have a granite tabletop, for example, you'll often have things like this, although you may notice that you can have a very fine pattern or you can have a more chunky pattern. And they're both going to be granite, and they're both going to have quartz and the feldspar and other kinds of things in there, which include the muscovite and biotite that are in there along the way. Then we have our ways in which igneous rocks form. And you can sort of see, again, more temperatures, lower temperatures get us up into the feldspar areas. The higher temperatures get us into the olivine areas. Then this sort of shows the volcanic structures that we have. We have the magma underneath, which will flow up. There are different types of volcanoes. We'll cover different types of volcanoes later, but sometimes we have flows and sometimes we have explosive processes that happen, and different rocks can form from that. Then we have our good old sedimentary rocks. About 75% of all rock outcrops on the continents are sedimentary. This is sort of sediment is sort of build up over time. So you can, again, click on this link in your PowerPoint to see a little bit of a video. Here we have conglomerate rocks, sandstone, mudstone, siltstone. Guess what sandstone is made out of? Guess what mudstone is made out of? Guess what siltstone is made of? It's not really rocket science kinds of stuff along the way. We also call mudstone shale. So you might every now and then hear about different kinds of drilling and we get into shale drilling along the way. So a lot of these are rocks that are made up of particles and pieces that are done under pressure. Some have much bigger pieces, some have really, really tiny pieces. Silt and clay have extraordinarily tiny, tiny pieces along the way. And we don't often tend to think of clay as being in pieces, but in fact, it is. Sorry to interrupt things there. I heard a beeping going off in my kitchen, and it turns out my dinner, which I'm baking a turkey to eat for the next week because I'm single and I have an unadventurous life in terms of diet. So I'm just bake a turkey and I eat that for a week. So it's baking downstairs, and I didn't realize that it was about done and ready to be turned. So I apologize for the interruption. Now you know more about me than you wanted to know. But back to the rocks. Back to the rocks. Types of sedimentary rocks. Sometimes we do have organic rocks, much more so than we'll ever have in terms of minerals. Then we have chemical and biochemical kinds of rocks that are formed in different ways. In large part because quite frequently we will have these things formed in oceans or lakes or rivers, and these kinds of things will often have living creatures that will leave themselves behind that become part of this, especially if it's anything that develops a shell. Limestone, very common here in Indiana, is one of these kinds of sedimentary rocks. And if you look inside of the rocks, you'll often find little kinds of shell structures and little kinds of the leftovers of what was living before along the way. These are often very useful in terms of construction. We have lots of limestone buildings, for example, but these are often also things that are malleable enough that tools could be made. So you find a lot of arrowheads, for example, made out of sedimentary rocks. They're very simple to make. They're not as sturdy as perhaps an obsidian one would be, but it is also much easier to make. So if you don't need something that's going to be sort of top of the line, kind of sharper image arrowhead, but you're willing to go to Dollar General arrowhead, that would be this kind that's here as well. And we can see chalk. That's microscopic shells and clay. We don't tend to think you take a piece of chalk on, and it's like, okay, yeah, that has shells in it, very tiny, very fine kinds of things that are there along the way. But we also have things like halite and quartz that do get into the mineral area when we're dealing with this along the way. And then we have altered plant fragments when we're dealing with coal. Coal is, again, the dead dinosaurs, the leftovers. Usually it's not really dinosaurs so much as it is leftover vegetation. There's probably a dinosaur or two mixed in there somewhere along the way. So if as you're driving along, the gas gives you just a little bit of a kick, maybe there was a dinosaur, maybe there was a velociraptor somewhere in that gallon along the way. There are different types of coal. Some are better for different purposes. Bituminous coal, for example, here, it tends to be much better for furnaces, and use anthracite coal has strong industrial purposes along the way. Peat is not typically thought of as being a coal kind of structure, and yet there are places like in Scotland where you'll burn the peat, and that will what you'll be using rather than coal because it's there quite a lot. You can also use peat in the manufacturing of scotch and other liquors. So it's good to know which kinds of substances that are out there along the way. Lithification, what this is it's sort of a process of packing in. The lithosphere is the area around the surface of our planet where we live, but we're sort of living on top of it, and we're packing things in. So you take the different pieces, say clay or other minerals or shells or other kinds of things, and you push it down and you push the water out. And over time, pressure and time, if you remember Shawshank Redemption, what do you need for a diamond? You need carbon, pressure, and time. This is what happens here. Sometimes we have a more cementing which can happen if you've got things that are more grainy than are more particleized. In different rocks will have different pieces inside of them, some of which are more organized in structure. Minerals tend to be more organized in structure than other kinds of rocks. And as we're looking in sediment, we'll often also find our fossils. Our fossils are most frequently found in sedimentary rocks. They're not going to be found in igneous rocks so much. Why? Because igneous rocks, lava. What happens when you drop a living organism in lava? It obliterates, it melts, it incinerates. It's not going to leave a nice structure like this behind. So we're going to find most fossils in sedimentary rocks, not in our igneous rocks. And this is what gives us a great understanding of the pattern of life. Remember, 75% of our continental structures are sedimentary rocks, so we can find a lot of things in these different structures. So then we have metamorphic rocks, and metamorphic rocks are ones where something has happened to it to change. It typically under heating and extreme pressures that are different from what it originally formed. So something originally formed, but then something happened to it. So we have like the parent rock here, the shale, or the granodiorite here, which turns into our slate. Shale is rather flaky, easy to break apart. Slate is more tightly compact and harder along the way. And sometimes we can sort of see, look at this interesting design that is impressed upon our gneiss, this is pronounced gneiss rock here. So what a nice rock that we've got there. So heat, pressure, and then sometimes chemically active fluids. Water is chemically active, it will change things, but we might have other things that also can flow into the system and change the rock that's inside. You can see a video here which talks about that as well. Then we also have what's called foliation, which is a sort of a sort of pressing in. So we've got confining pressure that turns into a little bit of a different kind of pressure that takes place. And then we have the non-foliated texture, which is where we get differential stresses that will happen in weirder ways. So we have marble as perhaps the best example for a non-foliated structure. When you look at marble, you often have this pattern inside. We even call it marbling. Sometimes you'll have a stake and you look at it and you'll say, oh, that's nice marbling. Well, it's not really marbling, but we're taking that idea from the way the rocks work here. And you can look again here, different kinds of metamorphic rocks, including marble and our gneiss rock. You know, that's a nice rock. And our schist rock, say that properly, say that carefully. Our slate here. Notice what's happening here. This is a slate quarry. As you break the rocks apart, notice they come apart in square chunks. Obviously, this one is very square, others are not quite so, but it's coming apart not just as pebbles and not just as stones. It's not just a stone quarry. So you're getting interesting structure here, and then you can make slate roofs and slate tabletops and other ways that it ends up being used. Then here we have a schist rock that has some garnet crystals inside of it that have become sort of mixed in and locked in. So those are important. We have very important metallic minerals. We use obviously gold, silver, copper for monetary purposes and other kinds of ornamental processes. We also use silver and copper in quite a number of other uses, like silver for tooth fillings, for example, copper for wiring, and copper was often used for roofing purposes or drainage purposes. When copper began to become more valuable, people who had copper fixtures on their buildings would often find those stolen along the way. So we find a lot of these things in different kinds of what we would call vein deposits. So you sort of go underground and you sort of see them almost embedded like a vein in the environment, inside of the tunnel, or as you're doing the strip mining, you sort of find it again and again and again. through that. It tends to be deposited in different ways. So they tend to be harder to find. In terms of what we use in terms of our own country, this is the chart in terms of what it says annual per capita, that means per person usage of what's going on. Didn't know how much you use, did you? How much do we use in terms of coal? How much do we use in terms of petroleum? How much do we use in terms of iron? Who uses that much iron? And we're not even talking about weightlifters here. Along the way. But there's a lot of stuff that goes into manufacturing the stuff that we use. It goes into manufacturing and producing the food, the clothing, the buildings, the roads, everything that we use, including the energy, the heating, the electricity, getting water from one place to another. So all of these things are very, very important for the ongoing structure of our economy. So what we want to do is figure out where we can find things. And there are some things that are easily found. There are some things that are more difficult to find. And what we often find, like here in the Grand Canyon, we'll find mixtures. We have quartz and feldspar that are sort of combined together in these different kinds of deposits. So when we're using these different things, we see we have non-metallic and we have metallic elements that will give us different industrial uses. We take advantage of the different physical and chemical properties. Some things burn easily, some things do not. Some things, like most diamonds in the world, are not used, for example, for ornamentation, for jewelry. Most diamonds are actually used industrially, and they're mostly used for drills. I have diamonds in my house. Don't break in and steal them, because I have 2 diamonds that I know of in my house, and they're both in the needle on my record player. And one is in there, and then I have a backup, because even diamonds eventually wear out. So that becomes important. We have lots and lots of coal here in the United States. We are the sort of the Saudi Arabia of coal. We've got it all over the Midwest. We've got a lot of it in the Western country. Anthracite coal and the bituminous coal tends to be the most important in terms of energy producing and industrial uses. The other types here are less useful for that, but they still have uses as well. Notice the anthracite coal has the highest BTU, that stands for British Thermal Unit, which means that as you burn it, you get more heat per pound from anthracite than you would from the others. But notice the bituminous coal here is very close behind, and we've got lots and lots and lots of that that's here. So that we also have quite a bit of oil and natural gas in our country, although we've drained quite a bit of it over the last century and a half. So there are also massive reserves that are more easily accessible right now in places like Venezuela, Saudi Arabia, even Russia and Canada. It is a myth to think that we get most of our foreign oil from Saudi Arabia. The United States gets most of its natural gas and oil imports, if we import anything at all, from Canada and Mexico. Those are our 2 biggest import places. So we do a lot of trade with them because they're closer. It's easier to get to. Most of the oil from the Middle East, Saudi Arabia, Kuwait, the other countries in the area go to either Japan or to India or to Europe. Again, because that's the closer trade routes that are there along the way. But we can find different places in our features to find oil and natural gas. And this sort of gives you an example of what we might see in different structures. We have gas and oil, often found together. There's a place in Indiana called Gas City. And Gas City was once called Harrisburg, but it got renamed Gas City because they literally would put torches into the ground that would let the gas off, and they would burn it. And it would burn and burn and burn and burn so brightly it could be seen for dozens of miles in every direction. So they renamed it Gas City. They burned off hundreds of years, potentially, of natural gas to get to the oil underneath, because they didn't have a use for the natural gas at that time than they did for the oil. Well, the oil's gone and now the natural gas is too. Guess where that natural gas went? You guessed it. This is why the climate is acting up the way it is. We've been doing that kind of stuff. We've been taking the gases that are under the ground and putting them into the atmosphere now for a long time, not just 50 years, not just 100 years. We've been doing this for quite a while along the way. So we can find it in different parts, and it's hard to always determine exactly where the oil is and exactly where the gas is. No matter how well our technology gets, you can put a well down and get the wrong thing. Also, it changes things. When you're drilling for oil, what happens to the top up here when that oil disappears? Well, sometimes you get different kinds of earthquakes and shifting kinds of stuff. And one of the processes that's been happening lately is called fracking. And that's where you force water in to push oil up and around. And surprise, surprise, a lot of places that have been doing this have been registering lots and lots and lots of relatively minor but still damaging earthquakes. Oklahoma's had hundreds and hundreds of additional earthquakes in a very short amount of time due to this along the way. So here we can sort of see where it's talking about fracking, the processes that are here. When oil prices are really high, then this becomes economically viable. When oil prices are really low, this process is too expensive to be really useful. So right now, because oil prices are relatively low, because our economy is depressed thanks to COVID, but even before then, our oil prices were actually pretty low. We haven't had $4 gallons of gas for quite a long time. It's been $2 to $3, and then it dropped down to under $2. Well, that's because the places where it's easy to get oil ramped up their production. So fracking and other kinds of processes like that really aren't worth doing unless you can charge $3, $4, or even $5 a gallon for gas, or equivalent oil prices for other processes like industrial stuff like that. So a lot of that stuff has shut down or really cut back for a while, which is not necessarily a bad thing. It might be a temporarily bad thing for people employed in those industries. But in the long term, A, we're not releasing the stuff into the atmosphere, but B, we're also not using it up as fast. And we have a chance to find other alternatives before we use it all up. Because one day or another, we're going to need to find another alternative, because again, as Robin Williams would say, they're not making any more dead dinosaurs. And I'll see you in the next lecture.